Hi there in Buenos Aires. If everything went well, we probably had some live conversation. This is instead the video recording of the talk I prepared for you. Basically, it was a bit too risky and also late in Italy for a live session, and anyway, in my house the connection sometimes is not excellent, so better instead to record the video to make sure that the video is good enough for you. So today we are going to talk about a few of the Redis 6 features. Basically, so far the biggest things in Redis 6 are probably RESP 3. That's the new protocol, and we are not going to talk about that because it was covered quite enough in the past in general, and also I feel like you will have more time to be exposed to that. It's more interesting, in my opinion, to talk about the other three different features. One is ACLs, access control lists. Another one is threaded I/O. This is, chronologically speaking, the latest one that was implemented. ACL is like 90% ready. Threaded I/O is like 100% ready, at least in the form we want to ship it in Redis 6. And the final one is the new Expire. The new Expire, it's actually the old Expire, the one that everybody already knows in Redis for 10 years at this point, but just the implementation, the internals are very different because the system we used was not perfect. However, for 10 years it allowed Redis to like survive, and now it's really time to bring something better to the table. The new Expire is 0% implemented. However, all the design is there, and it's one of such features that you have to code a lot, to change a lot of internals, but otherwise it's not something so difficult to do. There are no big design challenges, and most of the design is already done. So here we already have inside the unstable branch, and this will land inside the unstable in I will start working at it in the next days, so I hope in a matter of a few weeks we should have it. Okay, so let's start for ACLs. For this, probably it's better to start with a terminal because I want to show you. Okay, let's start actually with the history. Okay, this is the suggested, the example Redis configuration file. As you probably know, when you didn't want to expose some command because it's too dangerous to users, you used to use this rename command configuration directive, so you could actually change the name of the command to one which is unguessable from the outside world. So still for operations you can use this now very odd command name, but the other users cannot guess it, so it's impossible to use. For example, in a cloud environment, if you rent an instance to some user, it's not possible to call config or debug or other commands that are dangerous. This kind of worked for some time, but of course it's a very limited system in order to guarantee a different level of accesses. Why you want different level of accesses? One is because of security. It's the corporate use case. Like we are a lot of people, there are many Redis instances. We want to be sure that certain people have just access to a given amount of features in the Redis server and maybe a subset of the keys and so forth. But there is another interesting use case that probably is more applicable to a number of applications, also to smaller environments, which is just safety from the point of view of the operations. So, for example, I download a new library in order to implement something with Redis. For example, I don't know, like request limits to limit the requests per second of certain objects. I have already an instance of Redis running. I want to reuse this in order to throttle the number of requests you can do to given objects. And maybe I'm not sure about this new library I downloaded. I don't want to perform a very complete security auditing in the code. What I can do is to use for this library a user that can just run a very limited set of commands. In this way, if for example the library is bugged, or just for testing, maybe calls flush all or other commands that can disrupt the production of the instance, there is no risk. So basically ACLs are also very useful in order to isolate what bugs or other problems in the code can create as operational problems in the Redis instance. There was to find a reasonable user interface in order to implement ACLs in Redis. Basically everything is exposed via the ACL command. You can do many things, but the most interesting thing is setting users. So set user, for example, anti-reds. I have to, and then I have a set of freeform options I can give to the user. I start with on, because normally the user is off. So for safety, you know, the default is always that you cannot do anything, and you have to enable the user to do things. And then I want to set to list the number of commands that this user can call, and I will just add get and ACL itself. And then I have to specify a pattern of keys this user can access. I can specify multiple patterns, but in this case I want just the user to be able to access every key, and then I can set one password, foobar. I can set multiple passwords if I want, so you can rotate passwords, and that should be it. Okay. Now if I call ACL list, I can see that there is a new user, and I can also see that there is another user, which is the default user. The default user is used in order to understand what new connections can do before they are authenticated. If you want the old Redis behavior, you just have a default connection that can do everything. And if instead you want a less permissive, a more strict security in your instance, you can disable the default user, and in that case people have to authenticate with out in order to do something, to claim to be aware of some user in the system. The out command, in the old form it was out password. Now it accepts an extended form, which is out username and password. Now I am authenticated, and at this point, because I enabled the anti-reds user to just use the set command, if I try the get command, if I try set, it should be denied, but get should work. However, as you can see, it's very stressful to specify every single command, get, ACL, and so forth. So actually, let's return back to the default user. I can use no password with the default user because the default user has had this special flag no pass. You may want to avoid having this in the default user. This is basically the configuration is completely backward compatible with Redis 5, but you can use more strict configurations. So I have categories. Those are all the categories that I have defined inside Redis, and each category defines a subset of the Redis commands. For example, I want to see what is the dangerous category. And it includes all the stuff that normally you don't want normal users to be able to call, like psing, write, administration commands, very slow commands that can create problems, swap db and stuff like that. Let's check another one. The read category is all the commands that can just read without ever writing something to the server. So when I define the user, I can say ACL set user antireds plus read plus connection, which is another category with connection management commands. In this way, basically, I modified what the Redis user was already be able to do. If I want to start from scratch, usually I do ACL set user antireds reset, and then I write the other things, the other directives. Basically, the ACL rules are processed left to right. So reset will completely reset completely the user, and then all the other things will be added. Now this user doesn't have the on switch, so, and has no password, so if I try to authenticate, I will just get an error and so forth. Okay, I guess you got the idea. Oh, an interesting thing is that you can also have ACLs on subcommands like that. Okay, I want the antireds user to be able to call debug segfault, but not the other debug subcommands. So you can control the keys, what keys are accessible using multiple patterns. You can control the commands, the subcommands. You have quite control on what the user can do. However, you may think that this creates an overhead in the Redis server, so makes Redis slower. Well, fortunately, that's not the case because of the implementation. So let's jump to the whiteboard in order to show how it is implemented. Let's start with a clear canvas. Basically, Redis already has a user structure. Now, after ACLs, has a user structure, and the user defines basically a bitmap with each bit corresponds to a given command. So if a bit is set, a given command is enabled. If instead is clear, another command is denied, cannot be executed. So basically, to check for this condition is extremely fast. Just every Redis connection has an associated user. So for example, it's associated with antireds. So when the connection wants to do something, we check against the antireds user if a given bit is set, and so forth. From the point of view of patterns, there is a small penalty to pay from the point of view of performances. However, if you just enable all the keys, which is basically the asterisk, we set a given flag in the user, which is called all keys, so we can skip completely the test. This also happens if all the bits are set. Here in the command bitmap, we enable all commands bit in order to make sure we can skip the test when it is not useful. Long story short, basically you cannot, using the Redis benchmark, there is no way to see a difference between ACLs and not ACLs unless you specify a big number of subcommands, and then you benchmark exactly calling the subcommand. Otherwise, the penalty is not incurred at all. You, in order to have a penalty for subcommands, you have to call the subcommand. And usually, the subcommands that you want to deny are in the configuration side. So commands that are called in very rare situations. So in general, there is a very small penalty here. Just another thing, I've shown you the use of the ACL command, but you can also use a configuration file, which is exactly using an external LCL file. You specify an LCL file, and then you have, once this is specified, you can use basically SEL load and also SEL, there is also SEL save, but it was not listed here for an error. But you can save and load the new ACLs. An interesting thing is that when you load the ACLs, if there is an error in the ACL file, all the old users are preserved, so the half-loaded state is discarded. So only if the configuration, the ACL configuration is completely legal, it will be loaded. Otherwise, there will be no, because otherwise you can introduce a security bug. For example, you specify certain rules and then the strict rules are not loaded because there was an error in the middle. Okay, basically that's it, and of course this is enforced also in the Lua scripts and so forth. Let's go for the other feature, which is threaded IOs. So in general, there is this conversation in the community about if Redis should be threaded or not. Well, let's make a few arguments about that, because it's an interesting, legitimate topic. So this is a computer, okay? I hope that also in Buenos Aires computers are like round and not squared. So the computer at this point has multiple cores, and yeah, it sounds strange that Redis can just run here if there is all the remaining cake outside. However, the problem with that approach is the approach of trying to use all the cores by having a thread in the implementation of Redis is that basically you have to fight very hard in order to make sure that actually a threaded implementation can use all the cores. And there is another problem. Once you tried to do that, and it's impossible unless you use a shared nothing architecture, with the current semantic of Redis you have to have locks in the data structures, because in different threads you can have clients accessing the same key and the same data structure. So in general it's very hard to make it very scalable under a given limit. And there is a bigger problem, that you at some point add another computer, number 2, and then what you do, because the threaded implementation cannot scale in the other node as well. So you have to run anyway another instance here, and you have to face with the key partitions problems and replication and all the usual distributed computing stuff. So the idea so far was like, instead what we do is we have multiple cores and we just run different Redis instances for each of this core. This makes operations more complex. However, the big advantage is that we have a truly shared nothing architecture. So if Redis can deliver 1 million operations per second, it will deliver 1 million in this core, 1 million in the other core, and 1 million in the other core. On top of that, Redis will be much simpler. And one of the reasons Redis is so stable, is reliable, doesn't crash, doesn't have a lot of bugs, is because it's simple. It's not because we are smarter than the other developers. Just we may be a bit more humble and say, okay, if I make it very complex, probably it will be a total piece of shit. So reduce the complexity instead, and it's a possible approach. You know, not the only approach, but it's a reasonable way to think. Moreover, this approach of having basically a cluster inside one instance is scalable because you say, okay, I just will continue with that. So the idea is to stress a bit more about Redis cluster. To make a good cluster, you need a good client. So the first thing that we are doing is to create a proxy. Actually, the proxy is already quite working. Fabio Nicotra, which is a friend of mine that works at Redis Labs, is working at the proxy. And yes, today he fixed the last critical bug, and now we see it working very, very, very well. Basically, it's like 90% of performance of hitting directly Redis itself. However, the proxy is multi-threaded because creating a multi-threaded proxy is not so hard. So the complexity of the multi-threading was put in the proxy. If you have just a normal client, normal Redis client, the client can talk to the proxy, and the proxy will abstract away the Redis cluster protocol. So that's our idea. However, there was a very low-hanging fruit, which is the following. If you profile Redis, you will see that if this is the total execution time, oh, sorry, this is very terrible rectangle. like 50% of this execution time is mostly the write system call with some of the read system call, but mostly is the write system call. So if you don't use pipelining, a lot of resources are spent here just in the write system call. So if this cannot be accelerated without using threads, if not with a lot of complexity, maybe we can accelerate this. And if we accelerate this 10 times, because we use multiple cores in order to serve just the writes, suddenly, from the point of view of the execution time, it's like if this was taking 5%. So we can just making Redis use a total of 55% of the time it uses, and this means basically to double the performance that the server is capable to run. So what we can do basically in order to make this very, very, very simple, so simple which to the extent to be trivial to avoid introducing bugs. So, okay, Redis is single-threaded, does all the things, the event loop, blah, blah, everything single-threaded. At some point, it executes all the commands, still completely a linear process. And then we reach this interesting spot. We have the buffers in the clients that are ready to be sent, one to one client, one to the other. And here we fan out to multiple threads. So here there is thread 1, thread 2, thread 3, just in order to serve the clients, to just take the buffer and send it to the socket. And then once this process has ended, we return back single-threaded and we continue the execution again in a sequential way. In this way, basically, the software continues to be completely one thread for all the important things, but we fan out to multiple threads just in the interesting spot. However, this is more complex to implement than it looks like, because how do you coordinate the threads in order to avoid that you waste more resources in the coordination compared to the gain that you have? Well, the problem is that if you use mutex signal conditions, the usual pthread stuff, you will see that a lot of the gains is burned in the coordination. So instead you can use spin locks. However, if you use spin locks and you have multiple threads here locking, they are, even when they are not used because there is low traffic in the server, there are just a few parallel clients, you are burning a lot of CPU cycles, 100% of a core each time, and this is unacceptable. It's also not very good for the environment because you are burning a lot of energy without any reason. So instead, what happens is that each I/O thread spins, but from time to time it enters a given code path when it tries to acquire a mutex. So basically we have a way in order to stop an I/O thread and make it sleep and resume it when it's needed. So if we have just a few clients, we just use a single thread to do anything. Once the clients become a significant number, we start the I/O threads, process fan out to the I/O threads and return single-threaded. However, once the number of clients drop, immediately we return single-threaded. So the threads will keep spinning only when there are a big number of clients. There is actually need for that. With this implementation, we can easily go from, for example, 117 IOPS to something like 320 or something. Basically, it's possible to get 2x the performance of Redis by using, for example, 4 or 5 additional cores. Having more and more cores doesn't make sense because you can speed up anyway only the 50% of Redis, and so if you speed up it enough, making it faster and faster will not make a huge difference because the other 50% will keep running at the same speed. And threaded I/O are already implemented and can be used if needed. Of course, if it's possible, it's much better to use pipelining, because with pipelining you solve the problem in a direct way, basically, because what happens is that using pipelining with a given read system call, you read a number of commands, then Redis will process all the commands sequentially and put all the replies in the output buffer, and then it will call a single write if there is enough space in the kernel output buffer of the socket in order to deliver the replies. So we just, with pipelining, call a lot less write system calls and read system calls, and the problem is solved at the root. Okay, let's jump to the final feature, which is the new Expire algorithm. So in the past we did something like that. You have basically an hash table where the keys are stored. For here there is A equals 5 and B equals some list object or whatever. If I set an expire to A with expire A 3 seconds, I use an additional hash table which has just the expires. So here it becomes A equal the Unix time basically at which the key will expire. So if somebody requests this object here with get A, I check if it has an expire. If it has, I check if the expire is already elapsed. And if so, I delete the object and it will return null to the client because the key A is no longer there. However, what happens if E was set, an expire was set, but then nobody will ever ask about A again for a long time? I cannot take this memory used just because nobody is requesting this object, which is logically gone. So what I do is something that is right now. What Redis does is random sampling. Basically, from time to time, every tick inside the server, I check here random keys. Check here, check here, check here. Let's find if there is some key which is expired, and then I found finally A. Oh, this is expired, and I delete it. So basically, the garbage collection of expired objects is performed in two ways. One way is basically lazy, which is when an object is requested, I check. The other way is active. I have to spend some CPU time in order to try to check if there are objects which are already expired. However, expiring by random sampling is not great because, for example, I can have multiple keys here that are not expired, and just there is an object here which already expired, and I'm wasting a lot of CPU and never finding A, if I'm lucky. So it creates a lot of problems. How it's possible to improve this algorithm? Well, clearly you need some kind of ordered data structure. So we still have the hash table where there are the keys stored, and then instead of the hash table we use a radix tree in order to record the keys for expire time. So for example, if this will expire in 1 second is the first object, then there is another one that will expire in 5 seconds, and then after 100 seconds there is this object. So if I want basically to expire things, I don't have to resort to random sampling. I just start from here and I say, is this already expired? Okay. Is this already expired? Okay. This expired? No. So I just have a sequential list of objects that could be expired, and if a given one is not expired yet, all the following will not be expired. However, there is a problem with that. In order to order the data structure like that, I have to use as keys the expire time followed by the object name. It means that it's no longer possible to look up A from the radix tree without also knowing the Unix time at which it will expire, because the key in the radix tree will be this whole thing. So in the other side I have to take some information about A. Okay, I still want to remember what is its value, but also I want A to remember the Unix time at which it will expire. And also I want to know if A will expire or not, because it's possible that there is a key without an expire set. So basically, the solution was to redesign completely the key object. So this time we have an expire field. In the past we used basically SDS strings in order to represent keys in the main hash table of the Redis keys. Now instead it will be replaced by this structure that you see. So we have an explicit expire, and this is also handy when, in order to implement the TTL command, the other commands. Once the key object is looked up, we already have this information, like if the key is an expire, when it will expire, and so forth. This is also useful in order to implement lazy expiring, lazy garbage collection of expire without checking the radix tree, because we have the information here at this point. And then there is the key len. Then there are all the other fields that we already had, like LRU, LFU, in order to perform max memory eviction. And finally, we have along the side of mine, this wine, flags, 8 flags, 8 bits of flags in the key object directly. 1 bit is used in order to remember if actually the key has or not an expire, and the other bits can be used in the future in order to implement more advanced features. Also, if this flag, probably the expire will end being here at the end. Okay, this structure is invalid, but basically it will be stored logically at the end of the structure. In this way, if the flags don't include the expire bit, I can avoid, when I allocate the key object, I can avoid to allocate these 8 bits. So it's also important in order to make sure that the new system will not use more memory than the old system. So basically, this new system will make the expiration process a lot smoother. 1. It will no longer require that certain percentage of already logically expired keys will remain in memory. Why they did? Because at some point, when most of the keys are still not expired, in order to reclaim the latest 3-4% of keys that are expired, we need to scan too much slots, and it's too CPU costly. So at some point the algorithm right now stops scanning if there is too much work to do in order to make progresses. It will be faster, will use less CPU, it will be more precise, because now it's possible that a given key that is logically expired for 3 minutes ago was yet not evicted, and instead one that is expired just for 1 second is evicted. And because Redis has a notification in PubSub that you can enable in order to see the stream of the expired keys, this was not great. Now you can use the Redis server, for example, as a source of timers. You set a key and then you listen in the PubSub channel, and you get a notification when a given key expired, and at this point this will be more precise. So in general, big improvements in that side. This is also the kind of improvements I like more, because they are not user visible. The API is exactly like it was, but in general Redis will work better. Okay, that's all. I hope you got some new information you didn't already know from the Redis internals, and what Redis 6 will have that you may like. And I hope you a great continuation of your meeting. I should probably also join you sooner or later in Buenos Aires, when I will feel like I want to travel more. For now, it's better to stay here in Sicily because I traveled too much. But have a nice time and enjoy the rest of the event. Bye. See you on Twitter, GitHub, or whatever. Bye bye.